Tonight, we're going to explore something that will completely change how you understand the universe around you. We're going to discover how humanity learned to see what eyes cannot see, to perceive light that passes through our bodies without leaving a trace, to witness the most violent and energetic events in the cosmos. We're going to understand the Chandra X-ray Observatory, a machine floating in the darkness of space that reveals an invisible universe blazing with energy. By the end of this journey, you're going to understand how a telescope the size of a bus, orbiting thousands of miles above Earth, opened our eyes to black holes devouring stars, galaxies colliding in slow motion across eons, and the scattered remains of exploded suns still glowing with the heat of their final moments. Before we start, if you enjoy these deep explorations of space and the machines we've built to understand it, a quick like or subscribe would really help the channel grow. Now let's begin our journey into the invisible universe. Close your eyes for a moment and imagine the universe you know. You see stars twinkling in the darkness. You see planets, moons, and the faint smudge of the Milky Way arcing across the sky. You see nebulae glowing with the light of newborn stars. You see distant galaxies, faint points of light that have traveled billions of years to reach your eyes. This is the visible universe, the cosmos as revealed by optical telescopes and human eyes. It's beautiful, magnificent, and utterly incomplete. Now imagine another universe, overlapping the same space but invisible to your eyes. A universe where black holes shine brighter than entire galaxies, where the space between stars glows with gas heated to tens of millions of degrees, where dead stars pulse like cosmic lighthouses, beaming radiation across thousands of light years, where galaxies collide and their hot gas slams together in shockwaves that would dwarf our entire solar system. This is the X-ray universe, and until we learned to see it, we understood only a fraction of what's actually out there. X-rays are a form of electromagnetic radiation, part of the same spectrum as the visible light you see with your eyes, but with much higher energy. The energy of a photon, a particle of light, depends on its wavelength. Long wavelengths have low energy. Radio waves, with wavelengths measured in meters or even kilometers, carry very little energy per photon. Visible light, with wavelengths around 500 nanometers or about 500 billionths of a meter, carries moderate energy. Ultraviolet light has shorter wavelengths and higher energy. X-rays have wavelengths around 1 nanometer or less, which means each X-ray photon carries hundreds or thousands of times more energy than a visible light photon. This high energy means X-rays interact with matter differently than visible light. They can pass through substances that block visible light completely. A visible light photon trying to pass through your body gets absorbed or scattered almost immediately. X-ray photons, however, can pass straight through soft tissue. They're absorbed by denser materials like bone and metal, which is why X-rays reveal fractures and swallowed objects in medical imaging. This same property makes X-rays valuable in astronomy, but it also creates a fundamental problem. Earth's atmosphere absorbs X-rays. The same atmospheric layer that protects us from harmful solar radiation also blocks cosmic X-rays from reaching the ground. For billions of years of life on Earth, the X-ray universe remained completely hidden. To observe X-rays from space, you need to get above the atmosphere. You need rockets, satellites, and space-based observatories. The history of X-ray astronomy is therefore intimately tied to the history of the space age. It's a story that begins with captured German V-2 rockets in the New Mexico desert, continues through the tense years of the Cold War and the space race, and culminates with machines like Chandra, orbiting far beyond the protective blanket of air that shields Earth's surface. The X-ray universe, when finally revealed, turned out to be more violent and energetic than anyone had imagined. Gas clouds glowing at temperatures of tens of millions of degrees, black holes with masses millions or billions of times that of our sun, tearing apart stars and galaxies with their immense gravity. Neutron stars spinning hundreds of times per second, their magnetic fields a trillion times stronger than any magnet on Earth. The remnants of supernova explosions still expanding outward at thousands of kilometers per second, their edges glowing with the energy of the shockwave plowing through space. This is the universe Chandra shows us, a cosmos that exists alongside the one we see with visible light, but operates on completely different principles and reveals entirely different phenomena. The Chandra X-ray Observatory is named after Subramanian Chandrasekhar, an Indian-American astrophysicist who spent his career studying the physics of stars and their ultimate fates. Chandrasekhar, known to his colleagues as Chandra, which means moon or luminous in Sanskrit, made fundamental contributions to our understanding of stellar evolution. His most famous work established the mass limit for white dwarf stars. He showed that a white dwarf, the dense core left behind when a star like the Sun exhausts its nuclear fuel, cannot exceed about 1.4 solar masses. Beyond this limit, the Chandrasekhar limit, the star's gravity overcomes the quantum pressure supporting it, and it collapses further, becoming either a neutron star or a black hole. This work, published in the 1930s when Chandrasekhar was still in his 20s, earned him the Nobel Prize in Physics in 1983. It's fitting that a telescope designed to study the most extreme states of matter in the universe bears his name. Chandra is one of NASA's great observatories, a fleet of 4 flagship space telescopes launched between 1990 and 2003 to observe the universe across different wavelengths. The Hubble Space Telescope, launched in 1990, observes primarily invisible and ultraviolet light. The Compton Gamma Ray Observatory, operational from 1991 to 2000, studied the highest energy radiation in the cosmos. The Spitzer Space Telescope, launched in 2003 and operational until 2020, observed in infrared light, revealing cool dust and distant galaxies. And Chandra, launched in 1999, observes in X-rays. Together, these observatories provided humanity with unprecedented views of the universe across the entire electromagnetic spectrum, each revealing phenomena invisible to the others. Chandra's capabilities are extraordinary. It can detect X-ray sources 100 times fainter than any previous X-ray telescope. Its angular resolution, the ability to distinguish 2 closely spaced objects as separate, is about 0.5 arcseconds. An arcsecond is 1/3600th of a degree. To put this in perspective, if you could use Chandra to look at Earth from the moon, it could resolve objects about half a mile apart. This resolution is roughly 1,000 times better than the first X-ray telescopes flown in the 1970s. The sharpness of Chandra's vision allows it to see details in cosmic X-ray sources that were previously impossible to resolve, distinguishing individual objects in crowded fields, mapping the structure of supernova remnants, and pinpointing the locations of black holes in distant galaxies. The observatory itself is enormous, roughly 45 feet long with its sunshade deployed, weighing about 50,000 pounds at launch, including its booster. It orbits Earth in a highly elliptical path, ranging from about 10,000 kilometers at its closest approach to 140,000 kilometers at its most distant point, roughly one-third of the way to the Moon. This orbit takes 64 hours and 18 minutes to complete. The elliptical orbit serves several purposes. It keeps Chandra above Earth's radiation belts for most of its orbit, about 85% of the time. These belts, regions of trapped charged particles surrounding Earth, can damage sensitive instruments and create background noise in detectors. By staying above them, Chandra minimizes this interference. The high orbit also allows for long, uninterrupted observations, unlike telescopes in low Earth orbit that pass into Earth's shadow. Every 90 minutes or so, Chandra can observe a single target continuously for more than 50 hours, essential for studying faint or variable sources. But to understand Chandra, to truly appreciate what it's accomplished and what its potential loss would mean, we need to go back to the beginning. We need to understand how X-ray astronomy was born, how scientists first detected these invisible photons from space, and how those early discoveries laid the foundation for everything that followed. The story begins on a hot June day in 1962 in the desert of New Mexico. A team of scientists from American Science and Engineering, a small research company in Cambridge, Massachusetts, prepared to launch an Aerobee sounding rocket from White Sands Missile Range. The rocket stood ready, a slender cylinder about 13 meters long, painted white against the desert sun. Inside its nose cone sat a payload, unlike anything flown before, an X-ray detector designed by physicist Frank Paolini, sensitive enough to detect the faint X-rays the team hoped might exist beyond our solar system. The leader of this team was Riccardo Giacconi, a young Italian-American physicist who had been thinking about X-ray astronomy for several years. The idea had been proposed by Bruno Rossi, a professor at MIT and board chairman at American Science and Engineering. Rossi had suggested that the Moon, illuminated by the sun, might reflect some of the sun's X-ray emissions. If the team could detect these reflected X-rays, it would prove that space-based X-ray astronomy was feasible. The U.S. Air Force, interested in any technology that might have military applications during the Cold War, had provided funding, but almost no one expected to find X-rays from stars or other cosmic objects. The sun emits X-rays, yes, but it's a special case. The sun's atmosphere, its corona, reaches temperatures exceeding 1 million degrees, hot enough to produce X-rays, but the sun's X-ray output is minuscule compared to its visible light output. To produce detectable X-rays from a distance of light years, a star would need to emit far more X-ray energy than the sun. Most astronomers thought this was unlikely. Stars, they believed, were primarily optical objects. The X-ray universe, if it existed at all, would be dark and quiet. Giacconi and his team weren't so sure. They had built their detector to be 100 times more sensitive than any previous X-ray instrument. They had designed it with a wide field of view to increase the chances of detecting something, anything from the sky. And on June 18, 1962, at just before midnight, the rocket launched. The flight lasted only about 6 minutes above the 100-kilometer altitude, where Earth's atmosphere becomes thin enough to allow X-rays through. During those precious minutes, the detector scanned the sky, recording photons. Then the rocket fell back to Earth, its data preserved on film inside the payload. When Giacconi and his colleagues retrieved the payload and developed the film, they found something unexpected. The detector had recorded a very strong peak of X-ray emission. After weeks of analysis back at their laboratory in Cambridge, they reached a surprising conclusion. The signal was real. It wasn't an equipment malfunction. It wasn't from the moon. It was from a cosmic source of X-rays of truly staggering proportions. From the depths of space came X-rays so intense that they exceeded the sun's entire energy output by a factor of 100, and exceeded its X-ray output by a factor of about 100 million. It was a completely new type of object. They named it Scorpius X-1, the first X-ray source discovered in the constellation Scorpius. The discovery was announced in a paper published in Physical Review Letters in December 1962, titled Evidence for X-rays from Sources Outside the Solar System. This paper, as one historian later put it, launched 1,000 ships. The discovery of Scorpius X-1 meant that the X-ray universe was not dark and quiet. It was ablaze with energy. Somewhere out there in the constellation Scorpius, about 9,000 light-years from Earth, something was generating X-rays at a prodigious rate. But what? What could possibly produce such intense X-ray emission? The search was on to find the optical counterpart, the visible star associated with this X-ray source. The answer came in 1966, when astronomers identified a faint blue star at the position of Scorpius X-1. It was completely unremarkable, invisible light, an obscure object that had been photographed many times over the decades without anyone paying it much attention. But in X-rays, it blazed brighter than anything else in the sky, except the sun. Theorists quickly proposed an explanation. Scorpius X-1 is a binary star system. One component is a normal star, not particularly massive, only about 0.42 times the mass of the sun. The other component is a neutron star, an incredibly dense object, about 1.4 times the mass of the sun, but only about 20 kilometers across. Neutron stars are the collapsed cores of massive stars that have exploded as supernovae. They're so dense that a teaspoon of neutron star material would weigh about 1 billion tons. In the Scorpius X-1 system, the neutron star's intense gravity pulls matter off its companion star. This stolen material doesn't fall directly onto the neutron star. Instead, it forms an accretion disk, a swirling maelstrom of gas spiraling inward. As the gas spirals closer to the neutron star, it accelerates to tremendous speeds, approaching a significant fraction of the speed of light. Friction between particles in this disk heats the gas to tens of millions of degrees. At these temperatures, the gas emits X-rays copiously. The X-rays we detect from Scorpius X-1 come from this inferno of superheated gas being consumed by the neutron star. This discovery opened a new window onto the universe. If neutron stars in binary systems could produce such intense X-rays, then X-ray astronomy could be a powerful tool for studying these exotic objects, and neutron stars were just one possibility. black holes, objects so dense that not even light can escape their gravity, should produce similar X-ray signatures when they accrete matter from companion stars. The dam had burst. Rocket flight after rocket flight revealed more X-ray sources. Some were associated with supernova remnants, the expanding clouds of gas ejected when massive stars explode. Others were binary star systems like Scorpius X1. Still others remained mysterious, their nature unknown. Theoretical astrophysicists realized that the X-ray universe was a window onto extreme physics, revealing phenomena that simply don't occur in the everyday world or even in ordinary stars. The field of X-ray astronomy had been born, but rocket flights, while scientifically valuable, had severe limitations. Each flight lasted only minutes above the atmosphere. To truly survey the X-ray sky, to study individual sources in detail, astronomers needed satellites that could observe continuously over long periods. The first dedicated X-ray astronomy satellite was Uhuru, launched by NASA on December 12, 1970, from a platform off the coast of Kenya. The name Uhuru means freedom in Swahili, chosen because the launch coincided with Kenya's Independence Day celebrations. Uhuru carried a set of X-ray detectors that could scan the sky, building up a catalog of X-ray sources. Over its operational lifetime, Uhuru discovered hundreds of X-ray sources, expanding the known X-ray sky from a handful of objects to a rich population. Uhuru confirmed that many X-ray sources were binary star systems containing neutron stars or black holes. It discovered X-ray emission from hot gas in galaxy clusters, vast clouds of plasma heated to tens of millions of degrees by the gravitational energy of the cluster, and it found X-ray pulsars, neutron stars spinning rapidly and beaming X-rays like cosmic lighthouses. Throughout the 1970s, other countries launched their own X-ray satellites. The United Kingdom's Ariel 5, the Netherlands' ANS satellite, NASA's SAS-3, and others contributed to the growing understanding of the X-ray universe. Scientists discovered X-ray bursters, objects that flared suddenly in X-rays, sometimes increasing their brightness by factors of thousands in mere seconds. They found Seyfert galaxies, a class of galaxies with bright, compact cores that emit intense X-rays, likely powered by supermassive black holes. They discovered that Cygnus X1, one of the brightest X-ray sources in the sky, was probably a black hole. The first strong evidence for the existence of these objects, predicted by Einstein's general relativity. But all these early X-ray telescopes had significant limitations. They couldn't focus X-rays into sharp images the way optical telescopes focus visible light. Their detectors simply recorded X-rays, arriving from large areas of the sky. This meant they couldn't resolve fine details. If two X-ray sources were close together in the sky, these early telescopes couldn't tell them apart. The images they produced were blurry, with resolution measured in degrees or arc minutes, rather than the arc seconds achieved by optical telescopes. The breakthrough came with the Einstein Observatory, also known as MARJ HEAO2, launched by NASA in November 1978. Einstein was the first X-ray telescope that could actually focus X-rays to create sharp images. It used nested mirrors with special shapes designed by physicist Riccardo Giacconi and others to collect X-rays and bring them to a focus. The mirrors worked on a principle called grazing incidence reflection. X-rays, unlike visible light, penetrate most materials. If you tried to reflect an X-ray with a normal mirror, the photon would simply pass through the reflective coating and into the glass. But if you arrange for the X-ray to hit the mirror at a very shallow angle, almost parallel to the surface, then it will reflect rather than penetrate. Giacconi and his team designed mirrors in the shape of nested cylinders with carefully calculated curves, paraboloids, and hyperboloids that could collect X-rays arriving from a particular direction and focus them to a point. The Einstein Observatory revolutionized X-ray astronomy. Its images were sharp enough to resolve individual stars in star clusters, to map the structure of supernova remnants, to pinpoint the locations of X-ray sources in distant galaxies. It discovered that virtually all types of astronomical objects emit some X-rays. Stars even. Relatively cool stars, like the Sun, have hot coronas that produce X-rays. Young stars emit strong X-ray flares. White dwarfs in binary systems, accreting matter from companions, shine brightly in X-rays. Galaxies, clusters of galaxies, quasars, all turned out to have X-ray counterparts. The X-ray universe was not populated solely by exotic objects like neutron stars and black holes, though these were certainly the brightest sources. Instead, X-rays were a ubiquitous form of radiation produced by hot gas throughout the cosmos. Einstein operated for about 2.5 years before a system failure ended its mission in 1981. But the discoveries it made convinced the astronomical community that X-ray astronomy was essential to understanding the universe. When NASA began planning its Great Observatories program in the 1980s, an advanced X-ray facility was always part of the vision. That facility would eventually become Chandra, but the path from concept to launch would take more than 2 decades, involve thousands of people, cost billions of dollars, and require pushing the limits of what was technically possible. The story of how Chandra was built is a testament to human ingenuity and persistence. In 1976, Riccardo Giacconi and Harvey Tannenbaum submitted a proposal to NASA for a 1.2-meter X-ray telescope, an advanced facility that would push the capabilities of X-ray astronomy far beyond what Einstein could achieve. This proposal, initially called the Advanced X-ray Astrophysics Facility, or AXIAF, outlined an ambitious vision. The telescope would have mirrors polished to unprecedented smoothness, achieving an angular resolution of 0.5 arcseconds or better, about 25 times sharper than Einstein's best images. It would carry a suite of instruments capable of imaging, spectroscopy, and timing analysis. It would orbit above Earth's radiation belts, allowing for long, uninterrupted observations of faint sources. The scientific motivation was clear. Einstein had shown that X-ray astronomy could address fundamental questions about the universe. How do stars form and evolve? What are the properties of black holes and neutron stars? How did galaxies and clusters of galaxies assemble over cosmic time? What is the nature of dark matter? These questions couldn't be answered by optical astronomy alone. X-ray observations provided unique insights into high-energy processes, hot gas, and extreme gravitational fields. NASA approved preliminary work on XAF in 1977. Teams at Marshall Space Flight Center in Huntsville, Alabama, and the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, began studying the technical requirements and feasibility. The challenges were formidable. The heart of the problem was the mirrors. To achieve the desired angular resolution, The mirrors had to be extraordinarily smooth and precisely shaped. Optical telescope mirrors are polished until their surfaces deviate from the ideal shape by no more than a fraction of a wavelength of visible light, about 100 nanometers. For X-ray mirrors, the requirements were even more stringent because X-rays reflect only at grazing angles. Any imperfection in the mirror surface scatters X-rays in random directions, degrading the focus. The mirror design called for 4 nested pairs of mirrors, each pair consisting of a paraboloid and a hyperboloid, the configuration known as a Wolter Type 1 telescope. The mirrors would be made of a special glass ceramic called Zerodur, manufactured by Schott in Germany. Zerodur has an extremely low thermal expansion coefficient, meaning it doesn't change shape significantly when heated or cooled, essential for maintaining the precise mirror shape in the temperature variations of space. Each mirror segment had to be ground and polished to a smoothness of just a few atoms. The largest mirror segments were nearly 1.2 meters in diameter and about 0.8 meters long. After grinding and polishing, the mirrors would be coated with a thin layer of iridium, a metal chosen for its high reflectivity to X-rays and resistance to degradation in space. The company that won the contract to build these mirrors was Eastman Kodak, later taken over by ITT Industries. The grinding and polishing process took years. Technicians used computer-controlled machines to shape the glass, removing material molecule by molecule. The mirrors were tested at every stage using interferometry, a technique that uses the interference patterns of light waves to measure surface irregularities with atomic precision. The work required extraordinary patience and precision. A single error could ruin months of work. In parallel, teams worked on the scientific instruments. The observatory would carry 2 focal plane instruments, cameras that would sit at the focus of the mirrors to record the X-ray images. One instrument, the Advanced CCD Imaging Spectrometer, or ACIS, would use charge-coupled devices, the same type of detectors used in digital cameras, but specially designed for X-rays. ACIS would provide both images and spectra, measuring not just where X-rays came from, but also their energies, which reveals the temperature and composition of the emitting gas. The other focal plane instrument, the High Resolution Camera, or HRC, used a different technology based on microchannel plates. These are glass plates containing millions of tiny tubes, each about 1/8 the thickness of a human hair. When an X-ray strikes the inside of a tube, it knocks electrons loose, which cascade down the tube, creating a measurable electrical signal. The HRC would provide the sharpest images with spatial resolution better than 0.5 arcseconds and the fastest time resolution, able to track variations in X-ray brightness on timescales of microseconds. The observatory would also carry 2 transmission grating spectrometers, devices that could be inserted into the X-ray beam to spread the light into a spectrum, like a prism spreading visible light into a rainbow. These gratings, made of fine gold wires on a support structure, would allow detailed spectroscopic studies of bright X-ray sources, measuring emission and absorption lines from hot gas with high precision. Work continued through the 1980s, but progress was slow. NASA's budget for astrophysics was constrained by other priorities, including the development and repair of the Hubble Space Telescope. The Hubble, launched in 1990, suffered from a flaw in its primary mirror that blurred its images. The dramatic repair mission in 1993, in which shuttle astronauts installed corrective optics, absorbed significant resources and attention. In 1992, facing budget pressure, NASA made the difficult decision to descope AXAF. The original design had called for 6 mirror pairs, 12 individual mirrors in total, which would be too expensive to complete on the available budget. NASA cut this to 4 mirror pairs, 8 mirrors, reducing the collecting area but still maintaining the critical angular resolution. 2 of the 6 planned scientific instruments were also eliminated. These cuts reduced costs, but at the price of scientific capability. The observatory would collect fewer photons and provide fewer observing modes than originally envisioned. The descoping had another major consequence. The original plan had been to place AXAF in a low Earth orbit where it could be serviced by the Space Shuttle, similar to Hubble. With the budget cuts, NASA decided to change the orbit to a high elliptical path, reaching 1/3 of the way to the Moon. This orbit put the observatory permanently out of reach of the shuttle. There would be no possibility of repair missions or upgrades. AXAF had to work perfectly from the start, or the mission would be a failure. This raised the stakes enormously for the engineering teams. Every component had to be tested exhaustively on the ground because there would be no second chances. The descoped AXAF was assembled and tested by TRW, later acquired by Northrop Grumman at their facility in Redondo Beach, California. The assembly process was meticulous. The mirrors, arriving from various contractors, had to be precisely aligned and integrated into the high-resolution mirror assembly, the structure that held them in their nested configuration. The alignment tolerances were astonishing. The mirrors had to be positioned to accuracies of a few micrometers, about the width of a bacterial cell. In late 1996, the completed telescope was shipped to Marshall Space Flight Center for the final and most critical test, X-ray calibration. Marshall had built a unique facility for this purpose, a long tunnel where they could generate X-rays and test the telescope's response. Over 6 months, teams subjected the telescope to exhaustive testing, verifying that it met all performance requirements. They measured its angular resolution, its effective area at different X-ray energies, its point spread function, and countless other parameters. The tests confirmed what the team had hoped. The telescope worked. Its angular resolution was measured at 0.5 arcseconds, better than the specification. The mirrors were smooth enough, the alignment precise enough, the instruments sensitive enough to achieve the mission's scientific goals. In 1998, NASA held a contest to give AXAF a better name. More than 6,000 submissions poured in from around the world. The winners, a high school teacher and a student from different parts of the United States, both independently suggested naming the observatory after Subramanian Chandrasekhar. NASA Administrator Dan Golden announced the decision, noting that Chandrasekhar's work on stellar evolution and black holes made him an ideal namesake for an X-ray observatory. Thus, AXAF became the Chandra X-ray Observatory. The telescope was shipped to Kennedy Space Center in Florida in February 1999 for final preparations and integration with the Space Shuttle. The plan called for the shuttle to carry Chandra into low Earth orbit, release it, and then have Chandra use its own propulsion system to climb to its high working orbit. This required attaching a two-stage inertial upper stage rocket to Chandra, a combination that would make the payload the heaviest ever carried by the shuttle. All the pieces were in place. More than 2 decades of work by thousands of people, billions of dollars, and the hopes of the astronomical community rested on what would happen next. The shuttle Columbia sat on its launch pad, Chandra nestled in its payload bay. The launch window opened on July 23, 1999. The sky above Florida was clear on the morning of July 23, 1999. Inside Space Shuttle Columbia, the crew prepared for launch. Commander Eileen Collins would be making history as the first woman to command a shuttle mission. The other crew members, pilot Jeffrey Ashby and mission specialists Catherine Coleman, Stephen Hawley, and Michelle Tognini, had trained extensively for this mission. Their primary objective was to deploy Chandra and send it on its way to its working orbit. The countdown proceeded smoothly. At 12:31 a.m. Eastern Daylight Time, Columbia's main engines ignited, followed by the solid rocket boosters. The shuttle lifted off from Launch Pad 39B, its brilliant exhaust illuminating the night. The launch was spectacular, a pillar of fire rising into the darkness. About 5 seconds into the flight, something went wrong. Actually, 2 things went wrong simultaneously. First, an electrical short in some wiring disabled the primary controller on one main engine and the backup controller on another. The backup systems immediately took over, but if one more controller had failed, the mission would have faced a dangerous abort scenario. Second, and unknown to anyone at the time, a small gold pin inside the right main engine had broken loose during ignition. This pin, traveling like a bullet, struck the engine nozzle's inner wall and ruptured 3 hydrogen cooling tubes. Liquid hydrogen began streaming into the exhaust, creating a visible blue-green streak that nobody noticed during the launch, but showed up clearly in post-flight video analysis. The leaking hydrogen caused the engine's combustion chamber pressure to drop slightly. The engine's controller, sensing this, automatically opened the oxygen valves wider to compensate, which made the engine run hotter than normal. Meanwhile, all this extra oxygen consumption was depleting the external tank's supply faster than planned. The engines cut off about half a second early when the liquid oxygen ran out, leaving the shuttle with a velocity about 15 feet per second lower than intended. Not ideal, but the shuttle's orbital maneuvering engines could easily make up the difference. The crew reached orbit safely, though they wouldn't learn until after landing just how close the mission had come to disaster. Engineers later determined that if 5 cooling tubes had ruptured instead of 3, the nozzle would likely have failed catastrophically. Once in orbit, about 155 miles above Earth, the crew began preparing for Chandra's deployment. This required careful coordination. Chandra sat in Columbia's payload bay, secured by latches and umbilical connections that provided power and data links. The plan called for the crew to use the shuttle's robotic arm to lift Chandra out of the payload bay and release it. Then Chandra's inertial upper stage, a solid-fueled rocket, would fire twice to boost the observatory to its high elliptical orbit. On the mission's 5th day, the crew executed the deployment. Steve Hawley, operating the robotic arm, carefully lifted Chandra out of the payload bay and held it in position for final checks. The observatory looked like an enormous telescope, cylindrical and white, with solar arrays folded against its sides. Everything checked out. Hawley released Chandra into space. It drifted slowly away from Columbia, growing smaller against the black backdrop of space. About 45 minutes later, the inertial upper stage fired. The rocket burned for about 2 minutes, pushing Chandra into a higher orbit. Several hours later, the second stage fired again, further raising Chandra's orbit. Finally, after the inertial upper stage completed its burns, Chandra separated from it and began using its own smaller thrusters to fine-tune its trajectory. Over the next several days, additional thruster firings adjusted Chandra's orbit until it reached the desired elliptical path, perigee, or closest approach, at about 10,000 kilometers altitude, and apogee, or farthest point, at about 140,000 kilometers altitude. The orbital period settled at 64 hours and 18 minutes. Chandra would spend about 85% of its time above the harmful radiation belts that encircle Earth. On August 7, 1999, Chandra achieved its final orbit. The spacecraft was healthy, all systems functioning as designed, but the observatory's most critical component, its mirrors, remained protected behind a sunshade door, a large cover that shielded the delicate mirrors from contamination and stray light during launch and deployment. Opening this door was a one-way operation. Once opened, it could never be closed again. The team had to be absolutely certain that the spacecraft was ready. On August 12, 1999, 19 days after launch, the command was sent. Motors activated, and the sunshade door slowly swung open. For the first time, Chandra's mirrors looked out at the universe. The telescope was ready to begin its mission. The team selected Cassiopeia A as the target for first light. Cassiopeia A is a supernova remnant, the expanding debris cloud from a massive star that exploded roughly 3.5 centuries ago. By measuring the remnant's expansion rate and working backward, astronomers estimate the explosion occurred sometime between 1662 and 1680, most likely around 1667 to 1680. The explosion happened in our galaxy, about 11,000 light-years away in the constellation Cassiopeia. Curiously, despite occurring during an era of active astronomical observation, the supernova appears to have gone largely unrecorded, likely because thick interstellar dust dimmed the light to near invisibility from Earth's vantage point. Previous X-ray observations had shown that Cassiopeia A was bright in X-rays, making it an ideal test target. Chandra pointed its mirrors at Cassiopeia A and began collecting photons. The detectors recorded each arriving X-ray, building up an image over hours of observation. When the data was processed and the image displayed, the team saw immediately that Chandra had exceeded their expectations. The image showed an intricate structure of glowing filaments and knots, the shattered remains of the star spread across space. Different colors in the image represented X-rays of different energies, which in turn indicated different elements in the expanding debris. Red showed iron, green represented silicon and sulfur, blue revealed the highest energy X-rays from the shockwave. At the center of the remnant, right where the star had exploded, Chandra revealed a bright point source. This appeared to be the compact object left behind by the explosion, though at the time, astronomers couldn't yet determine whether it was a neutron star or a black hole. Previous telescopes hadn't been able to resolve it clearly. Chandra's image was so sharp that it showed the central object as a distinct point, separate from the surrounding debris. The first light image of Cassiopeia A was released to the public on August 26, 1999. It made headlines around the world. News organizations ran stories about NASA's newest observatory and the spectacular image it had captured. The astronomical community recognized immediately that Chandra would be transformative. The combination of high resolution and sensitivity meant that Chandra could study X-ray sources in unprecedented detail. The early months of Chandra's mission, often called the orbital checkout and calibration phase, involved systematic testing and verification of all the observatory's output systems and instruments. The team pointed Chandra at various calibration sources, objects with well-known properties, to verify that the instruments were measuring X-rays accurately. They tested all the observing modes, all the instrument configurations, making sure everything worked as designed. One early challenge arose with the ACUS instrument. During passages through Earth's radiation belts, high-energy particles struck the CCD detectors, causing damage that degraded their performance. The team quickly implemented a procedure to move ACIS out of the focal plane during radiation belt passages, protecting it from further damage. This added complexity to mission operations, but preserved the instrument's capabilities. By late September 1999, Chandra had completed its checkout and calibration and began routine science operations. Astronomers around the world had submitted proposals to use Chandra, and the best proposals had been selected through peer review. The telescope was booked solid with observations. The early science results confirmed Chandra's extraordinary capabilities. Observations of the Crab Nebula, another famous supernova remnant, revealed a never-before-seen ring around the central pulsar and jets of high-energy particles streaming outward at nearly the speed of light. Observations of the center of our galaxy detected X-ray flares from Sagittarius A star, the supermassive black hole at the Milky Way's core, providing direct evidence of its existence. Observations of distant galaxies revealed individual X-ray sources within them, allowing astronomers to study stellar populations and the environments around supermassive black holes in galaxies billions of light years away. Chandra was designed for a nominal mission lifetime of 5 years. The expectation was that by 2004, some critical component would fail, or the spacecraft would run out of propellant, or some other issue would end the mission. But Chandra, built to exacting standards with no possibility of repair, proved remarkably robust. Year after year, it continued to operate. In 2001, NASA extended the mission to 10 years. By 2004, when the nominal mission was supposed to end, Chandra was still performing flawlessly. The mission has been extended repeatedly since then. As of 2025, more than 25 years after launch, Chandra is still operating and still producing world-class science. This longevity is a testament to the quality of the engineering. The spacecraft's components have aged gracefully. The mirrors show no signs of degradation. The instruments, while not performing quite as well as when new due to accumulated radiation damage, still provide excellent data. The solar arrays still generate sufficient power. The gyroscopes and thrusters that control the spacecraft's pointing still function. Chandra has outlasted its design lifetime by a factor of 5, and shows no obvious reason it couldn't continue for several more years. But understanding Chandra's longevity and capabilities requires understanding how it actually works. How does this machine, floating in the vacuum of space, detect X-rays and turn them into the stunning images and spectra that have revolutionized astronomy? The answer lies in the observatory's extraordinary engineering. To understand how Chandra sees X-rays, we need to start with the fundamental problem. X-rays are very difficult to focus. In a typical optical telescope, light enters the telescope and strikes a curved mirror. The mirror's shape is carefully calculated so that all the light rays from a distant point source converge at a single point, the focus. This works because visible light reflects off mirrors at predictable angles following the law of reflection. The angle of incidence equals the angle of reflection. X-rays don't behave this way. If you tried to reflect an X-ray off a normal mirror at a perpendicular or near perpendicular angle, the X-ray photon would penetrate the mirror's surface and be absorbed rather than reflected. The photon has enough energy to ionize atoms in the mirror material and disappear into the bulk. But there's a way around this. If the X-ray strikes the mirror at a very shallow angle, almost parallel to the surface, then the photon can be reflected rather than absorbed. This is called grazing incidence reflection. The critical angle depends on the X-ray's energy and the mirror material, but for typical X-rays and materials like iridium or gold, the angle has to be less than about 1 or 2 degrees from parallel. This requirement completely changes the telescope design. You can't use a simple parabolic mirror like an optical telescope. Instead, you need mirrors shaped like segments of cones or cylinders, arranged so that X-rays graze their surfaces at shallow angles. The design that works best for X-ray telescopes is called a Wolter Type 1 configuration, invented by physicist Hans Wolter in 1952. A Wolter Type 1 telescope uses 2 reflecting surfaces in sequence. The first surface is a paraboloid, a shape derived from rotating a parabola around its axis. X-rays from a distant source arrive nearly parallel and strike the paraboloid at a grazing angle. The paraboloid reflects them, changing their direction slightly so they converge toward a focus. But after one reflection, the X-rays are still not perfectly focused. So they strike a second surface, a hyperboloid, which provides a second reflection that brings them to a sharp focus. This 2-reflection system, paraboloid followed by hyperboloid, achieves the same goal as a single parabolic mirror in an optical telescope. It brings parallel rays from a distant point source to a single focal point, but it does so using grazing incidence reflections that work for X-rays. Chandra uses 4 nested pairs of paraboloid hyperboloid mirrors. The mirrors are nested like barrels inside barrels, each successive pair slightly smaller in diameter. This nesting increases the collecting area. X-rays arriving from a source pass through all 4 pairs, and all 4 pairs focus the X-rays to the same focal point. The result is like having 4 telescopes stacked concentrically, all pointing at the same target and all bringing their collected X-rays to a common focus. The mirrors themselves are engineering marvels. Each mirror surface is a section of a cylinder with precisely calculated curves. The glass ceramic substrate, zero dur, was chosen for its extremely low thermal expansion. In space, the observatory experiences temperature variations as it moves in and out of sunlight, and as different parts of the spacecraft heat and cool. Any material that expands or contracts with temperature changes would distort the mirror shape and ruin the focus. Zerodur expands by less than 1 part in a million per degree Celsius, making it ideal for this application. The grinding and polishing process achieved a surface smoothness of about 2 nanometers, roughly the diameter of a few atoms. This level of smoothness is critical because any roughness scatters X-rays in random directions, degrading the image quality. After polishing, the mirrors were coated with a thin layer of iridium, about 20 nanometers thick. Iridium provides high reflectivity for X-rays and is resistant to oxidation and degradation in the space environment. The assembled mirror assembly, called the High Resolution Mirror Assembly, or HRMA, is about 3 meters long and 1.2 meters in diameter at its widest point. The total collecting area, the effective size of the opening through which X-rays can enter, is about 1,100 square centimeters at low energies, decreasing to a few hundred square centimeters at higher energies as the reflectivity falls off. The focal length, the distance from the mirrors to the focal point, is about 10 meters. This means the focal plane instruments sit about 10 meters behind the mirrors, a significant distance that required careful structural design to maintain alignment. Speaking of the focal plane instruments, these are where the X-rays are actually detected and measured. Chandra carries 2 primary instruments, ACES and HRC, mounted on a movable platform called the Science Instrument Module. Only one instrument can be at the focus at any given time. Before an observation, the Science Instrument Module slides one instrument or the other into position. A CIS, the Advanced CD imaging spectrometer, consists of 10 CCD chips arranged in 2 arrays. CCDs are solid-state detectors made of silicon, similar to those used in digital cameras but specially designed for X-ray detection. When an X-ray photon strikes the silicon, it ionizes many atoms, creating a cloud of electrons. The number of electrons created is proportional to the X-ray's energy. By counting these electrons, ACIS can measure both where the X-ray hit and how much energy it had. The 2 arrays in ACIS serve different purposes. One array, called ACIS-1, is optimized for imaging. It provides a wide field of view, useful for observing extended objects like supernova remnants or galaxy clusters. The other array, ACISS, is arranged in a linear configuration optimized for use with the transmission gratings for spectroscopy. A CIS operates at very cold temperatures, around minus 120 degrees Celsius, to reduce thermal noise. The detectors are sensitive to X-rays, with energies from about 0.2 to 10 kiloelectron volts. For comparison, a typical dental X-ray uses photons with energies around 50 kiloelectron volts, so Chandra detects softer, lower energy X-rays than those used in medicine. The other focal plane instrument, HRC, uses a completely different technology. HRC consists of 2 microchannel plate detectors. A microchannel plate is a thin glass plate, about the size of a dinner plate, containing millions of tiny tubes. Each tube is about 10 micrometers in diameter, roughly 1/8 the thickness of a human hair, and about 1.2 millimeters long. The inside of each tube is coated with a material that emits electrons when struck by radiation. When an X-ray photon hits the front of a microchannel plate, it strikes the inside of one of the tubes and knocks electrons loose. These electrons are accelerated down the tube by a high voltage applied across it. As the electrons travel down the tube, they strike the sides, knocking loose more electrons. This creates an avalanche, multiplying the original signal. By the time the electron cloud exits the tube, it contains about 30 million electrons, a measurable pulse. A grid of fine wires at the exit of the microchannel plate detects this pulse and determines which tube it came from, revealing where the original X-ray hit. This allows HRC to create images with very high spatial resolution, better than 0.5 arcseconds. HRC has two components. HRC-I provides wide field imaging similar to ACISI. HRCS is a linear array, designed for use with the low-energy transmission grating for spectroscopy. One advantage of HRC over ACIS is its faster time resolution. ACIS reads out its detectors every 3.3 seconds, which limits its ability to track rapid variations in X-ray brightness. HRC can measure variations on timescales of microseconds, making it ideal for studying objects like pulsars that vary rapidly. The third component of Chandra's instrument suite is the transmission gratings. There are two types: the high-energy transmission grating spectrometer, or HETGS, and the low-energy transmission grating spectrometer, or LETGS. Both work on the same principle as a diffraction grating in optics, but adapted for X-rays. A transmission grating is an array of very fine parallel wires or bars made of gold. The spacing between the bars is on the order of a fraction of a micrometer. When X-rays pass through this grating, they are diffracted, meaning their paths are bent by amounts that depend on their wavelength and therefore their energy. X-rays with different energies are diffracted by different amounts, spreading them out into a spectrum. The gratings are mounted on a support structure that can be inserted into the X-ray beam just behind the mirrors. When not in use, they're swung out of the way. When spectroscopy is needed, the appropriate grating is swung into position. The X-rays pass through the grating, get diffracted, and then travel to the focal plane where either ACIS or HRC detects them. Because the detector can measure exactly where each X-ray hits, and the grating has dispersed X-rays of different energies to different positions, the detector can reconstruct a high-resolution spectrum showing exactly how much X-ray emission comes from each narrow energy range. The HETGS is optimized for higher energy X-rays from about 0.4 to 10 kiloelectron volts. It actually consists of two types of gratings at slightly different orientations, creating an X-shaped diffraction pattern at the focal plane. This allows disambiguation of the spectrum. The LETGS covers lower energies from about 0.09 to 3 kiloelectron volts and provides the highest spectral resolution Chandra can achieve at soft X-ray energies. High-resolution spectroscopy is crucial for understanding the physical conditions in X-ray sources. The spectrum reveals emission lines from highly ionized atoms, absorption edges, where X-rays get absorbed by intervening material, and continuum emission from processes like thermal radiation and synchrotron emission. By analyzing these features, astronomers can determine temperatures, densities, chemical compositions, velocities, and magnetic field strengths in cosmic X-ray sources. The entire process of making an observation with Chandra is carefully orchestrated. Astronomers submit proposals describing what they want to observe and why. A peer review committee evaluates the proposals, and selects the best based on scientific merit. Approved observations are scheduled into Chandra's observing plan. When it's time for an observation, commands are uploaded to the spacecraft. The spacecraft uses its reaction wheels, large spinning wheels that can transfer angular momentum to the spacecraft to rotate and point the telescope at the target. An aspect camera, a small optical telescope mounted on Chandra, continuously monitors guide stars to ensure the pointing remains stable to within an arc second or better during the observation. The mirrors collect X-rays from the target and focus them onto whichever instrument is positioned at the focal plane. That instrument records the X-rays, measuring their positions, energies, and arrival times. The data is stored on board in a solid-state recorder and then transmitted to Earth during scheduled communication passes with NASA's Deep Space Network of antennas. On the ground, the Chandra X-ray Center in Cambridge, Massachusetts, receives the data and processes it. Processing includes removing instrumental artifacts, calibrating the energy measurements, correcting for known detector issues, and packaging the data in a format astronomers can use. The processed data is made available to the observers who proposed the observation. After a proprietary period, usually about a year, the data becomes public, available to any astronomer who wants to use it. This system has produced an enormous scientific legacy. Over 25 years, Chandra has observed thousands of individual objects and produced hundreds of thousands of exposures. The data archive contains information on everything from planets in our solar system to the most distant galaxies observable. Hundreds of papers are published each year based on Chandra observations. The discoveries span the entire range of astrophysics. One of Chandra's most important contributions has been to the study of supernova remnants, the expanding debris, clouds from exploded stars. These objects are critical to understanding stellar evolution, the production and distribution of chemical elements, and the physics of shockwaves and particle acceleration. Chandra's high resolution allows it to resolve fine details in supernova remnants that were invisible to previous telescopes. We've already mentioned Cassiopeia A, Chandra's first light target. Continued observations of Cass A have revealed an astonishing wealth of detail. The X-ray emission shows filaments, knots, and shells of different elements distributed unevenly throughout the remnant. The explosion that created Cass A was not symmetrical. Material rich in silicon and sulfur is concentrated in certain regions, while iron is found elsewhere. This distribution pattern suggests that the explosion mechanism involved complex three-dimensional instabilities, not a simple spherical blast. At the center of Cass A, Chandra has monitored the compact object. Years of observations have revealed its nature. It's a neutron star, its surface temperature decreasing measurably over the course of a decade. This cooling rate provides constraints on the properties of matter at nuclear densities, the physics of neutron star interiors, one of the few ways we have to probe these extreme conditions. Another famous supernova remnant is Tycho's supernova, named after the Danish astronomer Tycho Brahe, who observed it in 1572. Tycho was a Type 1a supernova, a different kind of explosion from Cass A. Type 1a supernovae occur when a white dwarf in a binary system accretes enough matter to exceed the Chandrasekhar limit and undergoes a runaway thermonuclear explosion. These explosions are used as standard candles to measure cosmic distances. Chandra's observations of Tycho's remnant have revealed intricate structures in the X-ray emission. One of the most striking discoveries was a pattern of stripes in the high-energy X-rays that traced the blast wave, the shock front expanding outward from the explosion. These stripes are thought to be related to the amplification of magnetic fields by cosmic ray particles accelerated at the shock front. The structure provides direct evidence for how shockwaves can accelerate particles to enormous energies, a process that contributes to the population of cosmic rays pervading our galaxy. Perhaps the most intensely studied supernova by Chandra is SN 1987A, a star that exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way. In February 1987, this was the closest supernova visible to the naked eye since Kepler's supernova in 1604. Astronomers around the world turned every available instrument toward it. Chandra has observed SN 1987A repeatedly over more than 2 decades, watching the remnant evolve in real time. When the star exploded, it ejected its outer layers at speeds of thousands of kilometers per second. This debris expanded outward, eventually slamming into a ring of gas that the star had ejected thousands of years earlier when it was a red giant. The collision between the fast-moving supernova debris and the slower-moving circumstellar material created shock waves that heat the gas to tens of millions of degrees, producing intense X-ray emission. Chandra's images have shown the X-ray emission brightening over the years as more of the debris reaches the ring. By 2010, the entire ring was glowing in X-rays. The observations have provided detailed measurements of the shock velocities, the mass of material involved, and the energy of the explosion. One of the biggest mysteries about SN 1987A has been the nature of the compact object left behind. When a massive star explodes as a supernova, the core collapses, and theory predicts it should form either a neutron star or a black hole. For SN 1987A, calculations suggest a neutron star should have formed, but for decades, no one could find it. Recent Chandra observations, combined with data from NASA's New-Star X-ray Telescope and the ALMA radio telescope, have finally provided strong evidence for the neutron star's existence. Chandra detected excess X-ray emission at the center of the remnant, right where the compact object should be. The emission is consistent with a young, energetic neutron star, possibly a pulsar, shrouded in dense material that makes direct detection difficult. If confirmed, this would be the youngest neutron star ever observed, born in an explosion witnessed by human eyes just a few decades ago. Supernova remnants are more than just beautiful objects. They're factories for heavy elements. When massive stars explode, the tremendous energy and high temperatures enable nuclear reactions that create elements heavier than iron. Things like cobalt, nickel, copper, zinc, and all the way up to uranium and plutonium. These elements are scattered into space by the explosion, mixing with the interstellar medium. Subsequent generations of stars form from this enriched material. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in supernova explosions billions of years ago and scattered through space before being incorporated into the cloud that formed our solar system. Chandra's ability to map the distribution of different elements in supernova remnants has confirmed this picture in exquisite detail. by measuring the energies of X-rays and identifying characteristic emission lines from different elements. Chandra can create maps showing where iron is concentrated, where silicon is found, where oxygen predominates. These maps reveal the three-dimensional structure of the explosion, providing clues to the explosion mechanism and the mass and composition of the progenitor star. Beyond our galaxy, Chandra has observed supernova remnants in other galaxies, cataloging their properties and evolution. In nearby galaxies like the Magellanic Clouds and M33, Chandra can resolve individual remnants and study them almost as well as those in our own galaxy. In more distant galaxies, Chandra can detect the brightest supernova remnants as point sources, providing statistical information about the supernova rate and the properties of the stellar populations. But of all Chandra's contributions to astrophysics, perhaps none has had more impact than its revelations about black holes. Black holes, objects so dense that not even light can escape their gravity, were purely theoretical until the late 20th century. Einstein's general theory of relativity, published in 1915, predicted their existence, but many physicists doubted they were real. The first strong observational evidence came in the 1970s with X-ray observations of Cygnus X1, a binary system where an unseen companion to a visible star appeared too massive to be a neutron star, implying it must be a black hole. Chandra has transformed our understanding of black holes by detecting them in extraordinary numbers and studying them in unprecedented detail. Black holes come in several varieties based on their mass. Stellar mass black holes, with masses ranging from a few to a few tens of times the mass of the Sun, form when massive stars collapse. Supermassive black holes, with masses of millions or billions of solar masses, lurk in the centers of galaxies. Intermediate mass black holes, if they exist, would fill the gap between these extremes. The way we detect black holes is primarily through their effect on surrounding material. A black hole in isolation, floating in empty space, would be essentially invisible. But black holes in binary systems, orbiting companion stars, can pull gas off those companions. The gas doesn't fall straight into the black hole. Instead, it forms an accretion disk, a swirling disk of material spiraling inward. As the gas spirals closer to the black hole, it accelerates to tremendous speeds. The friction between particles in the disk heats the gas to millions or even billions of degrees. At these temperatures, the gas emits X-rays copiously. This makes X-ray astronomy the premier tool for finding and studying black holes. Chandra, with its sharp vision, can pinpoint X-ray sources in distant galaxies, identifying them as likely black hole candidates based on their X-ray properties. One of Chandra's most important early discoveries was imaging the supermassive black hole at the center of our own galaxy, Sagittarius A star. Optical telescopes can't see the center of the galaxy because dust along the line of sight absorbs visible light. Infrared and radio observations can penetrate the dust, and they had shown that stars in the galactic center orbit something massive and compact at the position of Sagittarius A star. Measurements of stellar orbits indicated this invisible object has a mass of about 4 million suns confined to a region smaller than the orbit of Mercury. The only plausible explanation is a supermassive black hole. Chandra has observed Sagittarius A star many times, monitoring it for X-ray emission. Most of the time it's relatively quiet, emitting only faint X-rays from the hot gas in its vicinity. But occasionally, Chandra has caught it flaring, brightening by factors of 10 or more over the course of hours. These flares are thought to occur when material, perhaps a gas cloud or a disrupted asteroid, falls toward the black hole and gets heated to extreme temperatures before disappearing beyond the event horizon. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's event horizon, showing the supermassive black hole in the galaxy M87. That image was made using radio telescopes. Chandra has also observed M87 extensively, studying the enormous jets of particles and radiation that stream outward from the vicinity of the black hole. These jets, visible in radio, optical, and X-ray light, extend for thousands of light years, far beyond the galaxy itself. The X-ray emission from the jets comes from synchrotron radiation emitted by electrons, spiraling in magnetic fields at nearly the speed of light. Chandra's observations have revealed the structure of these jets in detail, showing knots and shocks where material is being accelerated. Supermassive black holes, like the one in M87, play a crucial role in galaxy evolution. When they actively accrete matter, they're called active galactic nuclei, or AGN. The energy released by the infalling matter can be tremendous, sometimes exceeding the luminosity of the entire host galaxy. This energy can heat the surrounding gas, drive powerful winds that blow material out of the galaxy, and suppress star formation. Chandra has found evidence for these processes in numerous galaxies. One of the most dramatic examples is the galaxy cluster RxJ 1532. Chandra observations revealed enormous cavities in the hot gas that fills the cluster, each cavity hundreds of thousands of light years across. These cavities were blown out by jets from the supermassive black hole at the center of the cluster's largest galaxy. This energy required to create these cavities is staggering, equivalent to the mass energy of millions of suns. Yet this is just one of many clusters where Chandra has found similar evidence of black hole feedback. This feedback has profound implications for cosmology and galaxy formation. Computer simulations of galaxy evolution that don't include black hole feedback produce galaxies that are too massive and have too much star formation. When the simulations include feedback, where energy from the central black hole heats and expels gas, the simulated galaxies match observations much better. This suggests that Chandra's observations have been crucial in establishing that this feedback really occurs and measuring how much energy is involved. Chandra has also discovered thousands of black holes in binary systems throughout our galaxy and nearby galaxies. These stellar mass black holes, orbiting companion stars, and accreting material from them appear as bright X-ray sources. By cataloging them and measuring their properties, astronomers can learn about the population of black holes, how common they are, and how they form. In the Andromeda Galaxy, Chandra has detected hundreds of X-ray sources, many of them black hole or neutron star binaries. Because Andromeda is relatively nearby, only 2.5 million light years away, Chandra can resolve individual sources throughout the galaxy. By studying these sources and comparing them to similar objects in the Milky Way, astronomers can test whether the stellar populations and environments in Andromeda are similar to our own. One particularly exciting class of objects Chandra has studied are ultraluminous X-ray sources, or ULXS. These are X-ray sources in other galaxies that are far too bright to be typical stellar mass black holes. They seem to be radiating at luminosities that exceed the Eddington limit, the maximum luminosity a spherically accreting black hole of a given mass can sustain. ULXS might be intermediate mass black holes, objects with masses of hundreds or thousands of suns, bridging the gap between stellar mass and supermassive black holes. Or they might be stellar mass black holes, accreting in unusual ways that allow them to exceed the Eddington limit. Chandra's observations have revealed that ULXS are a diverse population with a range of properties, and the debate about their nature continues. One of the most important contributions Chandra has made to cosmology came from observations of colliding galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, plus vast amounts of hot gas, all held together by gravity. When two galaxy clusters collide, the process unfolds over hundreds of millions or billions of years. The galaxies themselves mostly pass through each other without direct collisions because the distances between galaxies are so vast. But the hot gas in the clusters, which outweighs the galaxies themselves, does collide. The collision creates shockwaves and heats the gas even further, producing intense X-ray emission. Chandra has observed many colliding galaxy clusters, but one stands out as particularly important: the Bullet Cluster, officially designated 1 E0657-56. This cluster is actually two clusters that collided and passed through each other about 150 million years ago. Chandra's observations revealed the hot gas in the two clusters clearly separated in space, with a shock wave visible where the gas in one cluster plowed into the gas in the other. The cluster got its name because one of the gas clouds looks like a bullet in X-ray images, compressed by the collision. What makes the Bullet Cluster scientifically revolutionary is what it reveals about dark matter. Dark matter is the invisible substance that makes up about 85% of the matter in the universe. We can't see it directly because it doesn't emit, absorb, or scatter light, but we know it exists because of its gravitational effects. Galaxies rotate too fast for the gravity of their visible matter alone to hold them together. Clusters of galaxies contain more mass than we can see in stars and gas. The leading explanation is dark matter, some form of matter that interacts gravitationally but not electromagnetically. The Bullet Cluster provides some of the strongest evidence for dark matter's existence. Astronomers used gravitational lensing to map where the mass is in the cluster. Gravitational lensing is an effect predicted by general relativity, where mass bends space-time, and light traveling through that curved space-time follows a curved path. By measuring how the light from distant background galaxies is distorted as it passes through the cluster, astronomers can create a map of where the mass is. When they overlaid Chandra's X-ray image showing the hot gas with the lensing map showing the total mass, they found a remarkable mismatch. The hot gas, which contains most of the normal matter in the cluster, is concentrated in the collision region, where the two clusters' gas clouds slammed into each other. But the peak of the total mass is not in the collision region. Instead, it's offset, centered on the locations of the galaxies. This makes sense if most of the mass is dark matter. The dark matter, which doesn't interact electromagnetically, passed right through the collision without being slowed down, continuing on with the galaxies. The gas, which does interact electromagnetically, was slowed by drag forces during the collision, falling behind the dark matter and galaxies. The separation between the visible gas and the gravitational mass provides direct visual evidence that the majority of the cluster's mass is invisible dark matter. Alternative theories to dark matter, which propose modifying our theory of gravity rather than invoking new particles, have difficulty explaining the bullet cluster. These modified gravity theories generally predict that the gravitational field should be strongest, where the normal matter is. But in the bullet cluster, the gravity is strongest, where there's comparatively little normal matter, only dark matter. The bullet cluster has therefore become one of the key pieces of evidence favoring the dark matter hypothesis. Beyond individual clusters, Chandra has contributed to our understanding of the large-scale structure of the universe. The hot gas in galaxy clusters emits X-rays because it's heated by gravitational energy as the cluster forms and material falls in. By studying the X-ray properties of many clusters at different distances, corresponding to different times in cosmic history, astronomers can trace how clusters have grown over time. This provides constraints on cosmological parameters, like the density of matter in the universe and the nature of dark energy, the mysterious force causing the universe's expansion to accelerate. Chandra has also discovered the warm-hot intergalactic medium phase of gas predicted to exist in the cosmic web connecting galaxies and clusters. This gas, heated to temperatures of millions of degrees but not quite hot enough to emit X-rays copiously, had been difficult to detect. Chandra observations looking for absorption features in the X-ray spectra of distant sources have provided some of the best evidence for this gas, which could help account for the missing baryonic matter in the universe. The discoveries extend beyond supernova remnants, black holes, and galaxy clusters. Chandra has observed a vast range of cosmic phenomena, revealing unexpected aspects of objects throughout the universe. Neutron stars and pulsars have been prime targets. Neutron stars are the collapsed cores of massive stars, objects roughly 1.4 times the mass of the Sun compressed into a sphere only about 20 kilometers across. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars have intense gravitational and magnetic fields, and they often rotate rapidly, spinning tens or hundreds of times per second. Pulsars are neutron stars with strong magnetic fields and beams of radiation emerging from their magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams. If one of the beams happens to point toward Earth, we detect a pulse of radiation each time it sweeps past. Pulsars were first discovered in radio waves in 1967, but they also emit X-rays, and Chandra can detect them. Chandra has studied the Crab pulsar in exceptional detail. The Crab Nebula is a supernova remnant, the debris from a star that exploded in 1054 AD. At its center sits a pulsar spinning 30 times per second. Chandra images show a brilliant point of light at the pulsar's position, surrounded by a complex structure of rings and jets. These features are created by the pulsar's intense magnetic field and rotation, which generate a wind of high-energy particles flowing outward at nearly the speed of light. The wind interacts with the surrounding nebula, creating shockwaves, and accelerating particles to tremendous energies. Chandra has captured these structures in exquisite detail, revealing how the pulsar transfers energy to the nebula. Magnetars are an even more extreme type of neutron star. These objects have magnetic fields 1,000 trillion times stronger than Earth's field, the strongest magnetic fields known in the universe. Magnetars occasionally produce enormous flares, sudden releases of energy that can briefly outshine the entire X-ray sky. Chandra has observed several magnetars, studying their X-ray spectra and variability to understand the physics of these extreme objects. X-ray binary systems, where a neutron star or black hole orbits a normal star and accretes material from it, come in many varieties. High-mass X-ray binaries involve a compact object orbiting a massive star, often an O or B-type star. Low-mass X-ray binaries involve a compact object orbiting a less massive star, often something like the Sun or smaller. The accretion processes differ between these systems, and Chandra can study them in detail. In some X-ray binaries, Chandra has observed jets, narrow beams of particles and radiation streaming away from the compact object at relativistic speeds. These jets, analogous to the jets from supermassive black holes but on much smaller scales, provide laboratories for studying the physics of jet formation and particle acceleration. Chandra has also made unexpected discoveries in our own solar system. In 2014 and 2015, Chandra observed Pluto as part of a campaign supporting NASA's New Horizons spacecraft flyby. To everyone's surprise, Chandra detected X-rays from Pluto. Pluto has no atmosphere to speak of and no magnetic field, so the source of these X-rays was initially mysterious. Based on what we know about solar-wind interactions, the leading explanation is that X-rays are produced by interactions between the solar wind, the stream of charged particles from the Sun, and gases escaping from Pluto's thin atmosphere. Similar processes could potentially occur on other cold bodies in the outer solar system. Chandra has detected X-rays from Jupiter, Saturn, and their moons. Jupiter's X-rays come from auroras at its poles, produced when energetic particles from the Sun interact with Jupiter's magnetic field and atmosphere. The processes are analogous to Earth's auroras, but on a much grander scale. Chandra's observations have revealed pulsating X-ray hotspots in Jupiter's polar regions, providing insights into the dynamics of Jupiter's magnetosphere. Even more surprisingly, Chandra detected X-rays from Uranus in 2021. Uranus is so far from the Sun that solar X-rays striking it and being reflected back are unlikely to explain the observations. The X-rays might come from auroras or from processes in Uranus's unusual magnetic field, which is tilted dramatically relative to its rotation axis. These observations are still being analyzed and interpreted. Chandra has observed comets, detecting X-rays produced by interactions between the solar wind and gases in the comet's coma. It has studied asteroids, looking for X-ray emission that might reveal their composition or the presence of exosphere gases. The ability to detect X-rays from such a wide variety of objects, from planets and moons to distant galaxies, demonstrates the versatility of X-ray observations. In the realm of stellar astronomy, Chandra has provided insights into how stars form, evolve, and die. Young stars, still embedded in the gas clouds from which they formed, emit strong X-rays from their hot coronae and from powerful flares. Chandra observations of star-forming regions like the Orion Nebula have detected thousands of individual young stars, cataloging their properties and revealing that young stars are far more active in X-rays than mature stars like the Sun. These observations help astronomers understand the early evolution of stars and the role of magnetic fields in stellar activity. Massive stars, the O and B-type stars that are tens of times more massive than the Sun, emit X-rays from their powerful stellar winds. These winds, streams of gas flowing outward from the star at thousands of kilometers per second, contain shocks where material moving at different speeds collides, heating to X-ray emitting temperatures. Chandra has confirmed that these wind shocks are the source of X-ray emission in massive stars. When massive stars die as supernovae, they sometimes leave behind not neutron stars, but black holes. If the black hole is in a binary system, it can accrete matter from its companion, becoming a bright X-ray source. Chandra has found many such systems, contributing to the census of stellar mass black holes in our galaxy and nearby galaxies. White dwarfs, the endpoints of stellar evolution for stars like the Sun, can also be X-ray sources under certain conditions. In binary systems, where a white dwarf accretes matter from a companion, the infalling material can release gravitational energy, heating to X-ray temperatures. Some of these systems undergo periodic outbursts, called novae, where the accumulated material on the white dwarf's surface ignites in a thermonuclear explosion. Chandra has observed novae in various stages, tracking the evolution of the X-ray emission as the system returns to quiescence. Cataclysmic variables, a class of binary systems involving white dwarfs, show a variety of behaviors. Some are dwarf novae, undergoing regular outbursts. Others are polars, or intermediate polars, where the white dwarf has a strong magnetic field that channels the accreting material onto its magnetic poles. Chandra's observations have revealed the complex interplay between accretion, magnetic fields, and rotation in these systems. Even the Sun, our own star, has been observed by Chandra. These observations, though limited because Chandra is not designed to observe such a bright object, have provided calibration data and insights into solar coronal physics. But beyond all these discoveries, beyond the science and the spectacular images, Chandra represents something more fundamental. It represents humanity's drive to understand the universe, to see beyond the limits of our senses, to comprehend phenomena that occur on scales of time and space and energy far beyond everyday experience. For 25 years, Chandra has been operating nearly flawlessly, producing science that has transformed our understanding of the cosmos. Thousands of astronomers around the world have used its data. Hundreds of PhD theses have been written based on Chandra observations. The observatory has been cited in tens of thousands of scientific papers. Its images have appeared in textbooks, planetarium shows, and museums. It has inspired a generation of scientists and captured the public imagination. Yet despite this extraordinary legacy, despite its continued excellent performance, Chandra now faces an existential threat. In March 2024, NASA released its budget proposal for fiscal year 2025 and the following years. The proposal included drastic cuts to Chandra's operating budget. Chandra's budget in 2023 was approximately $68 million. This covered the cost of operating the spacecraft, maintaining the ground systems, processing the data, and supporting the science community. The 2025 budget proposal cut this to $41 million, a reduction of about 40%. The projections for subsequent years were even more dire, $26 million in 2026, remaining at that level through 2028, and dropping to just $5 million in 2029. At these funding levels, the Chandra X-ray Center, which operates the observatory, concluded that they could not sustain science operations. The proposed budget would force a shutdown of the mission. The announcement sent shockwaves through the astronomical community. Chandra had just received the highest rating, Tier 1, in NASA's 2022 Senior Review, an evaluation process that assesses the scientific productivity and health of operating missions. The review had recommended continued operations through 2025, noting some thermal management challenges, but praising the observatory's scientific output and cost-effectiveness. For NASA to propose terminating such a highly rated, productive mission came as a complete surprise to most astronomers. The justification given in the budget proposal cited thermal management issues. Over its 25 years in space, some of Chandra's components have degraded, requiring active management to maintain temperatures within acceptable ranges. This increases the complexity of scheduling observations and processing data, which increases operational costs. NASA stated that these costs had grown beyond what the agency could afford given overall budget constraints. But the Chandra team strongly disputed this characterization. In an open letter, Patrick Slane, director of the Chandra X-ray Center, pointed out that the thermal issues were manageable and had not significantly impacted the observatory's scientific capabilities. The team had developed procedures to work around the thermal constraints. Chandra was still producing world-class science. Its mirrors showed no degradation. Its instruments, while not performing quite as well as when new, were still excellent. There was no technical reason the mission couldn't continue for many more years. The real issue, it became clear, was not that Chandra was failing. The issue was NASA's overall budget. Congress had appropriated about $1 billion less than NASA requested for its science programs. With a significant shortfall, NASA faced difficult choices about where to cut. The agency decided to reduce funding for its older missions, including Chandra and the Hubble Space Telescope, to free up resources for newer priorities. The astronomical community reacted with outrage and dismay. More than 700 astronomers signed a letter to NASA requesting reconsideration of the decision. A grassroots campaign called SaveChandra.org organized to raise public awareness and lobby Congress. Scientists pointed out that Chandra is the only high-resolution X-ray telescope currently operating. If Chandra is shut down, the United States would have no capability to observe the X-ray universe with the resolution needed for cutting-edge science. Europe has XMM Newton, which is still operating, but XMM Newton has lower angular resolution than Chandra. It's a complementary facility, excellent for spectroscopy of extended sources, but it can't match Chandra's ability to resolve fine details. The proposed Chinese and European X-ray missions are years or decades away from launch. In a survey of X-ray astronomers, 60% indicated they would consider leaving the United States if Chandra was terminated, potentially ceding U.S. leadership in X-ray astronomy to other countries. This brain drain, combined with the loss of Chandra itself, would devastate the field. Members of Congress from states with significant connections to Chandra, particularly Massachusetts, where the Chandra X-ray Center is located, raised concerns with NASA. Senators Ed Markey and Elizabeth Warren, along with several representatives, questioned the decision and urged NASA to reconsider. In response to the outcry, NASA conducted a review in the summer of 2024 to examine whether there were ways to reduce Chandra's operating costs without shutting down the mission. The operations paradigm change. Review looked at various scenarios, including reducing the number of observations, limiting the types of observations, reducing science support, and other measures. The review concluded that while some cost reductions were possible, there was no way to sustain full science operations at the drastically reduced funding levels proposed for 2026 and beyond. Maintaining even minimal operations would require more funding than NASA's budget proposal provided. As of late 2024 and early 2025, Chandra's fate remains uncertain. Congressional action has restored some funding, allowing the observatory to continue operations through fiscal year 2025. But the long-term prognosis is unclear. NASA has indicated that decisions about future funding will depend on the final congressional budget appropriations and on a new senior review scheduled for 2025. The situation is frustrating for the scientific community because Chandra remains capable of groundbreaking science. In 2024, even amid the budget crisis, Chandra was making discoveries. It observed the aftermath of gravitational wave events, detections of merging black holes and neutron stars by the LIGO and Virgo gravitational wave observatories. These multi-messenger observations, combining gravitational waves with electromagnetic observations across the spectrum, are opening new windows on the universe. Chandra's X-ray data is crucial for understanding what happens during these cataclysmic events. Chandra has been monitoring the evolution of supernova remnants, tracking how they change over the years. It has discovered new X-ray transients, objects that suddenly brighten in X-rays due to explosive events or changing accretion rates. It has studied the hot gas in galaxy clusters, mapping temperature and density structures to understand cluster dynamics and the distribution of dark matter. All of this work would cease if the observatory is shut down. The potential loss of Chandra would affect not just current research, but future projects. Observations that require years of monitoring would be cut short. Proposals for new projects that need Chandra's unique capabilities couldn't be pursued. Graduate students and postdocs who had planned to work with Chandra data would need to find alternative projects. The institutional knowledge accumulated over 25 years of operations, the expertise in X-ray astronomy concentrated at the Chandra X-ray Center and in the community would dissipate. There are no planned replacements for Chandra in the near term. NASA's Decadal Survey for Astronomy in the 2020s proposed a new flagship X-ray mission called LINX, which would have capabilities far exceeding Chandra's. But LINX is only in the conceptual design phase and would not launch until the 2030s or 2040s at the earliest, if it's funded at all. In the meantime, if Chandra is shut down, there will be a gap of a decade or more with no high-resolution X-ray observations. The situation highlights the challenges facing NASA and space science more broadly. Developing and launching flagship missions takes decades and costs billions of dollars. Once launched, these missions often exceed their design lifetimes and continue producing valuable science for many years. But operating them costs money, and as missions age, their budgets compete with newer projects. NASA's Great Observatories program illustrates this. The Compton Gamma Ray Observatory was deliberately deorbited in 2000 when one of its gyroscopes failed, raising concerns about its ability to safely maintain orbit. The Spitzer Space Telescope was shut down in 2020 when its orbit drifted so far from Earth that communications became difficult. The Hubble Space Telescope and Chandra are the last two great observatories still operating, now more than 30 and 25 years old respectively. Both have been proposed for budget cuts, Hubble by about 10% and Chandra by 40% or more. At the same time, NASA is developing the Nancy Grace Roman Space Telescope, a next-generation infrared observatory, and has allocated initial funding for the Habitable Worlds Observatory, a future flagship mission to search for signs of life on exoplanets. These new missions are scientifically exciting and will address important questions, but their development costs money, and NASA's overall budget has not grown to match the ambitions. The result is a zero-sum situation where operating existing missions competes with developing new ones. NASA argues that it must balance supporting current operations with investing in the future. Critics counter that shutting down highly productive missions prematurely wastes the investment made in building them and squanders their scientific potential. For Chandra specifically, the ironies are many. The observatory was designed to operate for 5 years and has lasted 25. It was built with no possibility of servicing or repair and has nonetheless continued working reliably. It cost about $2 billion to develop and launch, spread over decades. Its annual operating cost, even at the full $68 million budget, is a small fraction of that initial investment. Shutting it down to save $20 or $30 million a year when it could continue producing science for perhaps another decade seems short-sighted to many scientists. But the decision ultimately isn't made by scientists. It's made by policymakers in NASA and Congress, balancing competing priorities and budget constraints. The fate of Chandra will be determined by broader questions about science funding, national priorities, and how we value fundamental research. Whatever happens, Chandra's legacy is assured. Over 25 years, it has observed the X-ray universe with unprecedented clarity. It has revealed the violent, energetic, extreme cosmos that exists alongside the gentle starlight visible to our eyes. It has shown us the aftermath of stellar explosions, the feeding frenzies of black holes, the collisions of galaxy clusters, and the ghostly glow of gas heated to tens of millions of degrees. It has helped prove the existence of dark matter, traced the evolution of galaxies, measured the properties of neutron stars, and discovered phenomena that weren't even imagined when the mission was conceived. The images Chandra has produced are not just scientifically valuable, they're beautiful. The false color images, where different X-ray energies are represented by different colors, reveal structures and patterns that would be invisible to the eye, even if we could see X-rays. Supernova remnants appear as intricate laceworks of glowing filaments. Galaxy clusters show vast clouds of gas shaped by invisible dark matter and sculpted by the energy from supermassive black holes. Stellar nurseries glow with the X-ray signatures of thousands of young stars. These images have been displayed in museums, featured in documentaries, and shared widely on social media. They've inspired countless people to learn more about astronomy and science. The Chandra team has even pioneered sonification, converting astronomical data into sound. Working with composers and musicians, they've created audio representations of Chandra images, allowing people to hear the data. The sound of the bullet cluster, the whistles and crashes of the Crab Nebula, the eerie tones of a supernova remnant. These sonifications make Chandra's data accessible in a new way, engaging people who might not connect with visual images alone. Chandra has also been a training ground for a generation of astronomers, engineers, and data analysts. Working with Chandra data requires expertise in X-ray physics, data analysis, instrumentation, and astrophysics. The people who've gained this expertise have gone on to work on other missions, teach at universities, and contribute to the broader scientific community. If Chandra shuts down, this community will partly disperse, and rebuilding it for future X-ray missions will take time and effort. Looking ahead, the future of X-ray astronomy depends on both preserving current capabilities and developing new ones. If Chandra continues operating, it will remain the premier high-resolution X-ray observatory, complementing other missions and providing unique data. If it's shut down, the field will lose a critical tool, but it won't disappear. Europe's XMM Newton, Japan's XR, ISM satellite, and other current and planned missions will continue to study the X-ray universe, albeit with different capabilities and limitations. In the longer term, next-generation X-ray missions are being planned. The European Space Agency has concepts for advanced X-ray observatories. China is developing its own X-ray missions. NASA's proposed Lynx mission, if funded and built, would surpass Chandra in every metric: larger collecting area, higher resolution, broader energy range, better spectroscopy. It would be to Chandra what Chandra was to Einstein, a leap forward that enables science not possible with current technology. But Lynx is decades away at best, and there's no guarantee it will be built. The X-ray universe won't wait. Stars continue to explode, black holes continue to consume matter, galaxy clusters continue to collide. These events happen on timescales of years to millions of years. Some phenomena we are monitoring with Chandra are changing on human timescales, evolving visibly over the decades of observation. If we stop watching, we'll miss crucial phases of their evolution. This is the tragedy of potentially losing Chandra. It's not that X-ray astronomy will cease to exist. It's that we'll lose the ability to see certain details, to answer certain questions, to make certain discoveries. We'll be flying partly blind, missing a crucial wavelength of light that reveals phenomena invisible to any other telescope. The story of Chandra is a story about human curiosity and ingenuity. It's about pushing the boundaries of technology to see things that were previously invisible. It's about the long, difficult process of turning scientific ideas into working instruments and then into new knowledge. It's about international collaboration, with scientists and engineers from many countries contributing to the mission's success. It's about the intersection of basic science and national priorities, of scientific excellence and political and budgetary realities. As we think about Chandra's uncertain future, it's worth remembering how it began. In 1962, a small team launched a rocket into the desert sky on a quest to detect X-rays from the moon. They found instead a cosmic X-ray source far brighter than anyone expected, opening a new window on the universe. That discovery led to decades of work, of building instruments and telescopes, of observations and theories, culminating in machines like Chandra that can see the X-ray universe in exquisite detail. The universe is vast, complex, and strange. Much of it is invisible to our eyes, revealing itself only through instruments that extend our senses. Chandra has been one such instrument, letting us see the hot, energetic, violent processes that shape cosmic evolution. It has shown us a universe more dynamic and more extreme than we imagined. Whatever the future holds, the past 25 years have demonstrated the value of X-ray astronomy and the power of missions like Chandra. The data Chandra has collected will be analyzed for decades to come. The discoveries it has made will be built upon by future generations of astronomers. The engineering achievements it represents will inform the design of future observatories. But most importantly, Chandra has changed how we understand our place in the cosmos. It has revealed that the universe is not a static backdrop, but a dynamic, evolving system. It has shown us that matter and energy take forms we can barely imagine, from the ultra-dense neutron stars to the infinitely dense singularities inside black holes. It has given us glimpses of the earliest galaxies and the largest structures in the universe. It has reminded us that there is always more to discover, that the universe holds secrets we've only begun to uncover. Riccardo Giacconi, who discovered the first cosmic X-ray source and championed the development of X-ray telescopes throughout his career, received the Nobel Prize in Physics in 2002 for his pioneering contributions to astrophysics. In his Nobel lecture, he reflected on the journey from those early rocket flights to observatories like Chandra. He spoke about the importance of pushing technology to its limits in service of scientific discovery. He noted that each new capability, each improvement in resolution or sensitivity, revealed unexpected phenomena that transformed our understanding, and he emphasized that the work was never finished, that each answer raised new questions, each discovery pointed toward new mysteries. Chandra embodies this spirit of exploration and discovery. It has answered some questions and revealed many more. It has shown us wonders we didn't know existed and hinted at phenomena we still don't understand. It has been a faithful servant of science, operating far beyond its design lifetime, returning data year after year, transforming our view of the universe. If you look up at the night sky tonight, you won't see Chandra. It's too small and too far away. A silent machine orbiting in the darkness, but it's there. Its mirrors pointed at some distant cosmic target. Its detectors recording X-rays that began their journey thousands or millions or billions of years ago. Those X-rays carry information about events and processes at the extremes of physics, encoded in their energies and arrival times and spatial distribution. Chandra captures them, measures them, and sends the data back to Earth, where astronomers decipher the messages. This is what telescopes do. They extend our reach across space and time. They let us witness events that occurred before humans existed. They show us places we can never visit. They reveal light our eyes cannot see. They transform invisible radiation into images and spectra we can study. They turn the mysterious into the comprehensible, the unknown into the known. Chandra has been doing this for a quarter century, and if we're fortunate, it will continue for years to come. But whether it operates for one more year or 10, its legacy is already secure. It has shown us the invisible universe, the cosmos in X-rays, the violent beauty of the high-energy sky. It has reminded us that reality is stranger and more wonderful than we imagine, that there are depths to the universe that reward exploration, that the quest to understand our place in the cosmos is one of humanity's noblest endeavors. Among the countless discoveries Chandra has made, some stand out for their profound impact on our understanding of the cosmos. The observation of the Perseus cluster revealed sound waves propagating through the hot gas, driven by energy from the central supermassive black hole. These are the deepest notes ever detected in the universe. A B-flat that is 57 octaves below middle C, far too low for human ears to hear, but detectable through the pressure waves they create in the intergalactic gas. The discovery demonstrated that black holes don't just consume matter. They regulate their environment, pumping energy into the surrounding gas and preventing it from cooling and forming new stars too quickly. Chandra's observations of the Vela pulsar wind nebula revealed intricate jet structures and arcs that show how a spinning neutron star can power an entire nebula. The pulsar, spinning 11 times per second, generates magnetic fields so strong they accelerate particles to nearly the speed of light. These particles flow outward, creating a wind that illuminates the surrounding material in X-rays. The structures Chandra revealed are constantly changing, showing the dynamic nature of pulsar wind nebulae. In the galaxy NGC 6240, Chandra made a startling discovery. Not one, but two supermassive black holes in the process of merging. The two black holes, each hundreds of millions of times the mass of the Sun, are spiraling toward each other, locked in a gravitational dance that will eventually result in their collision. This observation provided direct evidence that galaxy mergers can lead to black hole mergers, confirming predictions from theoretical models of galaxy evolution. Chandra has also contributed to understanding gamma-ray bursts, the most energetic explosions in the universe after the Big Bang. When a massive star collapses to form a black hole, or when two neutron stars merge, the resulting explosion can release in seconds as much energy as the Sun will emit over its entire lifetime. These explosions produce brief flashes of gamma rays, followed by afterglows that can be detected in X-rays, optical light, and radio waves. Chandra has observed dozens of gamma ray burst afterglows, tracking how they fade over days and weeks, providing crucial data about the explosion mechanism and the environment surrounding the burst. The observations of the Tycho supernova remnant deserve deeper examination. Tycho Brahe observed this supernova in 1572, at a time when the prevailing belief held that the heavens were unchanging and perfect. The appearance of a new star challenged this worldview and helped pave the way for modern astronomy. Chandra's observations, more than 4 centuries later, have revealed the physics of the explosion in extraordinary detail. The X-ray spectra show emission lines from silicon, sulfur, calcium, and iron, elements created in the explosion and distributed unevenly throughout the remnant. The asymmetry in the element distribution suggests that Type 1 supernovae, while remarkably uniform in their total energy output, and thus useful as standard candles for measuring cosmic distances, are not perfectly spherical explosions. Based on these observations, instabilities and asymmetries appear to affect how the material is ejected. The stripes observed in Tycho's remnant are particularly intriguing. These quasi-parallel bands of X-ray emission trace the shock front, where the expanding supernova debris is slamming into the surrounding interstellar medium. The stripes are thought to result from instabilities in the shock, perhaps related to the amplification of magnetic fields by cosmic ray particles. The spacing and orientation of the stripes provide clues about the magnetic field structure and the efficiency of particle acceleration at the shock front. These observations connect to fundamental questions in plasma physics about how shocks can accelerate particles to high energies, a process important not just in supernova remnants, but throughout the universe. Chandra's study of galaxy evolution has revealed that the universe's history is written in X-rays. By observing distant galaxies, Chandra looks back in time, seeing these systems as they appeared billions of years ago when the universe was younger. The X-ray emission from these galaxies comes primarily from their populations of X-ray binaries and from active galactic nuclei powered by supermassive black holes. By counting how many X-ray sources appear in galaxies at different cosmic epochs, astronomers can trace how the black hole and stellar populations have evolved over time. Fenjar. Surprising discovery was that supermassive black holes were more active in the past than they are today. In the early universe, when galaxies were still forming and merging frequently, supermassive black holes accreted matter at prodigious rates, shining as bright quasars. As the universe aged and galaxy mergers became less common, the supply of gas to feed the black holes diminished. Most supermassive black holes today are relatively quiescent, like Sagittarius A star at the center of the Milky Way, which accretes only small amounts of material. Based on Chandra's deep surveys, the evidence indicates that the peak of black hole growth occurred about 10 billion years ago, when the universe was about 1/4 its current age. The Chandra Deep Field observations represent some of the telescope's most important contributions. These are regions of sky observed for extremely long periods, up to several million seconds of exposure time, to detect the faintest possible X-ray sources. The Earth resulting images reveal thousands of distant galaxies and active galactic nuclei, creating a census of X-ray sources across cosmic time. These deep fields have been coordinated with observations by Hubble, Spitzer, and other telescopes, allowing multi-wavelength studies that provide complete pictures of galaxy evolution. Chandra has also made unexpected contributions to the search for dark energy, the mysterious force causing the universe's expansion to accelerate. By studying galaxy clusters at different distances, astronomers can measure how the number and properties of clusters change over time. This provides constraints on cosmological parameters, including the density of dark matter, the density of dark energy, and the equation of state of dark energy. Chandra's X-ray observations of hot gas and clusters are crucial for these studies because they allow precise measurements of cluster masses, which are needed to determine how cluster abundance has evolved. The observatory's contributions to multi-messenger astronomy have become increasingly important. When LIGO and Virgo detect gravitational waves from merging black holes or neutron stars, astronomers worldwide scramble to observe the events with electromagnetic telescopes. Chandra is often part of these campaigns, searching for X-ray counterparts to the gravitational wave sources. The most famous example is GW1 70817, the merger of two neutron stars detected in August 2017. Chandra observed the event 9 days after the merger, detecting X-ray emission that gradually brightened over the following months. The data suggest this emission came from material ejected during the merger, creating a shockwave as it plowed into the surrounding environment. The X-ray observations, combined with optical and radio data, allowed astronomers to piece together what happened during this cataclysmic event, and to measure fundamental properties like the viewing angle and the energy of the ejecta. Chandra's ability to detect individual X-ray sources in nearby galaxies has enabled population studies that reveal how stellar evolution and black hole formation differ in various environments. In the Andromeda Galaxy, Chandra has cataloged hundreds of X-ray sources, including neutron star and black hole binaries, supernova remnants, and superbubbles, created by multiple supernova explosions. By comparing these populations to similar objects in the Milky Way, astronomers can test whether stellar evolution proceeds the same way in different galaxies. The observations of stellar coronae and stellar flares have revealed that the Sun, while active, is relatively quiet compared to many other stars. Young stars, still contracting and settling onto the main sequence, undergo enormous flares that release millions of times more energy than the largest solar flares. These flares are driven by magnetic reconnection events, where tangled magnetic field lines suddenly snap and release stored energy. Chandra has observed flares on hundreds of young stars, measuring their energies, durations, and frequencies. These observations have implications for the habitability of planets around other stars. If a planet orbits a star that undergoes frequent, powerful flares, the intense radiation could strip away the planet's atmosphere, making it uninhabitable. Understanding stellar activity is therefore crucial for assessing which exoplanets might support life. The X-ray observations of white dwarfs in binary systems have revealed a complex landscape of accretion physics. When a white dwarf pulls material off a companion star, the material doesn't fall directly onto the white dwarf's surface. Instead, it forms an accretion disk. In systems where the white dwarf has a weak magnetic field, the disk extends all the way to the white dwarf's surface, and material spirals in gradually. In systems with strong magnetic fields, the field disrupts the inner disk, channeling material along field lines onto the white dwarf's magnetic poles. These different accretion geometries produce different X-ray signatures, which Chandra can distinguish. Over its 25 years of operation, Chandra has become more than just a telescope. It has become a fundamental tool for astrophysics, used in conjunction with other observatories to create comprehensive pictures of cosmic phenomena. When the James Webb Space Telescope observes a distant galaxy in infrared light, revealing its stellar populations and dust, Chandra can observe the same galaxy in X-rays, revealing its black holes and hot gas. Together, these observations tell the complete story of the galaxy's evolution. When radio telescopes detect jets from a quasar, Chandra can measure the X-ray emission from those jets, providing information about the particle acceleration and magnetic fields. When gravitational wave detectors pick up the signal from merging neutron stars, Chandra searches for the X-ray afterglow, contributing to multi-messenger. Observations that probe physics at the most extreme limits. The spacecraft itself has proven remarkably resilient. Engineers designed it to operate for 5 years, but careful management and some good fortune have extended its life to over 25 years. The mirrors, polished to atomic smoothness, show no degradation. The structure maintains its precise alignment. The solar arrays still generate adequate power. The detectors, while showing accumulated radiation damage, continue to function. The reaction wheels that control pointing have operated reliably. The thrusters that maintain the orbit still have propellant. The computers and communications systems continue working. The limiting factors are not catastrophic failures, but gradual aging and the increasing complexity of managing thermal issues. Those thermal issues arise because some components generate more heat than they did when new, while others have lost some ability to radiate heat away. The team manages this by carefully scheduling observations to avoid thermal extremes, sometimes limiting what targets can be observed and when. But this is a manageable constraint, not a mission-ending problem. With proper management, Chandra could continue operating for many more years, perhaps another decade or more. The potential loss of Chandra would create a gap in X-ray astronomy capabilities that would last until new missions become operational. The proposed Lynx mission, if funded and built, wouldn't launch until at least the 2030s or 2040s. In the meantime, the worldwide community of X-ray astronomers would lose access to high-resolution X-ray imaging. Research programs that depend on Chandra would have to be abandoned or significantly modified. Students training to become X-ray astronomers would have fewer opportunities to gain experience with real data. The United States, which has been a leader in X-ray astronomy since Giacone's pioneering rocket flights in the 1960s, would cede that leadership to other nations. The universe is out there, blazing with X-rays, pulsing with the energy of black holes and neutron stars, glowing with the heat of galaxy collisions, illuminated by the scattered remains of exploded suns. Chandra can see it. For now, that window remains open. Let us hope it stays that way. If you enjoyed this deep dive into the Chandra X-ray Observatory and the invisible universe it reveals, please consider liking this video and subscribing to the channel. Your support helps me continue creating these explorations of space, science, and the machines we've built to understand our cosmos. Until next time, keep looking up, and remember that the universe contains wonders beyond what our eyes can see, mysteries waiting to be solved, and stories written in invisible light across the sky.